Okay, so in this video, I'm going to go over some questions that I've assigned in a worksheet. They are vector addition questions that pertain to displacement and velocity, and for the most part, the vectors are at right angles. So if we look at this first question, we have somebody that is walking 11 kilometers due north from a camp, and then they walk 11 kilometers due east. And I want to know what's the total distance walked, as well as what is the total displacement of the hiker. So if we start off, we would draw vectors tip to tail. So we would do our first vector. I would draw it 11 kilometers north. So this would be 11 kilometers. I've drawn it in the north direction. The second vector, starting from the end of the first, would be due east, also at 11 kilometers. And so your total distance walked, so there's the path, that's the vector diagram up to that point. A wants to know the distance traveled. Well, the distance is like how many steps you took. It's just 11 kilometers and 11 more kilometers, so 22 kilometers. The displacement, however, for part B, displacement, and the symbol we use for displacement is going to be D with an arrow on it, because this is just distance. The displacement would be the resultant vector starting from the beginning of the first and ending at the end of the second. So the resultant would point in that direction. This resultant vector is going to be the displacement. And so looking at that, if they're at right angles, you're solving this like it is a right angle triangle. So 11 squared plus 11 squared in kilometers. So that's 242 is what r squared is, kilometers squared. And so you take the square root of 242, and we get that answer. So the square root of 242 comes out to like 15.6. Which the questions have two significant digits, so we'll write that as 16 kilometers. We'll round it to 2 digits. So that is not a proper displacement yet because we do not have the angle reported. If you're going to report a displacement, you have to give me not just the how far away it is, not just the magnitude of the vector, you've got to give me the direction as well. So for this one, even though it can be obvious if it looks like an isosceles triangle, if you want to know the angle, you do second function tangent of opposite over adjacent, 11 over 11, and that will give you 45 degrees, which was obvious because this is a isosceles triangle. If the sides are equal, then the angles are equal, and it has to be 45. So we would report the displacement as being 16 kilometers, and we would report our direction, square brackets for direction. First direction we went was north, then 45 degrees, then east. So our distance traveled, 22 kilometers. The displacement, however, is 16 kilometers away on a bearing of north, 45 degrees east. Okay, let's try another one. We have an explorer walking 13 kilometers east, and then 18 kilometers north, and then finally going 3 kilometers west. So we have 3 vectors that we're going to draw here. So I'm going to draw 13 kilometers to the east. Here's vector 1. From that point, I will go 18 north. We're going a bit of an angle there by accident. 18 kilometers north. And at the end of that, we would go 3 kilometers to the west. So if we're working out A, the distance traveled, again, the distance, D, is just the sum of each of the legs traveled. So 13 plus 18 plus 3. So the distance is 34 kilometers. No direction, it's just how many steps you took. To get the resultant, you go from the beginning of the first to the end of the second. This is our resultant vector. And we can break this triangle up. We can look at the vectors and realize that if you went 13 over, but then 3 back, this distance, this part of the triangle is 10. And clearly the vertical part of the triangle is still 18. So those are the sides that we use in our Pythagoras theorem to get our resultant. So r squared is going to be 18 squared plus 10 squared. And so taking the 18 squared and 10 squared and then taking the square root, you should get r equaling 21 kilometers when we round that off. Now again, you can't report a resultant without an angle. So you have to get the angle. Again, I will get the inverse tangent of the opposite side over the adjacent side. I'm doing second function tangent of 18 over 10, or 1.8, yields me an angle of about 61 degrees when I round off. And so my resultant vector is going to be reported as 21 kilometers, and my bearing would be first traveled east, then 61 degrees north. Distance is 34 kilometers. However, how far away you are from where you started is 21 kilometers at a bearing of east, 61 north. Okay, that's a standard hiker question. Now we have a standard motorboat flowing across a river. So a motorboat is heading due east across a river at 16 meters per second. So we have due east, 16 meters per second, here's vector 1. At the same time, the river is flowing north at 9 meters per second. And I want to know what's the resultant velocity of this boat. So you have two velocities happening at the same time. The resultant velocity is going to be the vector addition of those two v's, plus we'll need the angle. So to get the resultant, you're going to do r squared equals 16 squared plus 9 squared, and then you'll take the square root of those squares. So we get a resultant of about 18 meters per second. It comes out to, I think, like 18.4. And so if I round to two significant digits, we'll get that as 18 meters per second. And then if we calculate our angle, the angle is inverse tangent of 9 over 16. Taking second function tan, 9/16 yields me a angle of 29 degrees. So that means the angle here is 29. So writing for A, what's the resultant velocity? This is all A. The resultant velocity is going to be 18 meters per second, and the bearing is going to be east and 29 north. For part B now, they tell us that the river is 136 meters wide. So that's telling us the distance or the length, the width of the river. And I want to know, so distance of 136 meters, and we want to know the time to cross the river. Well, if you know that it is 136 meters across the river, the only way you can use your formula for time equals distance divided by speed, or displacement over velocity, is you've got to make sure you use the component of the speed that matches the direction that's traveled. You can't use the 18 meters per second because it's not traveling at 18 meters per second in this direction. So you have to use the component of the speed that's in the same direction as the distance. Technically, that distance is north, so you have to use the speed that's north. So you will take the distance of 136 meters, which is north, and divide by the speed of 9 meters per second, which is north, and that will give you the time. So the trick is choosing the proper speed to put in there. Whoa, wait a minute, sorry. Just drew my picture wrong. I've got my picture screwed up. So we know the river, I lost focus on my picture. The river bank is like this. The river's flowing that way. The 136 meters is across. Just caught myself here. The 136 meters is across, so it's not north, it's east. And the speed across the river is 16, not 9. Glad I just caught this. So time is still distance over speed. Distance is 136 and it's east, so you have to use the speed that's east, which is 16 meters per second. And so you can see like the directions of east would cancel out. And so if you did 136 divide by the 16, that's going to give you an answer of 8.5 seconds. And there's no direction for time. Okay, so I had my picture drawn wrong. The river is going east-west, and so the boat is also going east-west across that river. The water was flowing north, but that meant the width of the river was perpendicular to that. Okay, so this was all for part B of the question. Part C of the question then says, we return to what it's asking, how far downstream is the boat when it reaches the other side of the river? It wants to know how far this way do you go? So you want to work out the other distance, technically a displacement. You know that you travel for 8.5 seconds, and you know the velocity in that direction is 9 meters per second north. So if you want the displacement north, you're going to take velocity times time. So 9 meters per second north times 8.5 seconds is going to give you 9 and 8.5, 76.5 meters, and that direction is north. And if we were rounding that to two significant digits, I guess we'd say 77 meters north would be the displacement for C. Okay, so 2 more questions on this worksheet. Number 4, while flying due east at 120 kilometers per hour, an airplane is also carried north by a wind that's blowing at 45 kilometers per hour. What's the resultant velocity? So at one point you have a velocity 120, and I've drawn that to the east, kilometers per hour. At the same time, there is a velocity of 45 kilometers per hour. I'm not drawing them exact, but I am drawing it smaller than the 120. The resultant will go from the beginning of the first to the end of the second. So that will be my result. And the angle in here we'll need to calculate to give me the total resultant velocity. So simple Pythagoras, r squared equals 120 squared plus 45 squared. So if you take both of those and square them and then take the square root, you should get 128 kilometers per hour. And you do inverse tangent, opposite over adjacent, and that angle would come out to 21 degrees. So the resultant velocity, you could call it r vector or v vector, the resultant velocity would be 128 kilometers per hour, and the heading would be east 21 degrees north. Okay, our last question. A motorboat is traveling 8.5 meters per second and heads north across a river. Okay, so I'll draw this better this time. Okay, there's my river. We're traveling at 8.5 meters per second north across the river. If the water is flowing downstream east at 3.8 meters per second, so I'll draw that east at the end of the first vector. What is the resultant velocity of the boat, which means from beginning to end? This is my resultant with its angle. So we can work out for A, the resultant, so r squared is 8.5 squared plus 3.8 squared, and then take the square root. So that resultant would come out to 9.3 meters per second. We need to have an angle. To get the angle, again, inverse tan of opposite, which is 3.8, divide by adjacent, which is 8.5, and we get an angle that is 24 degrees. So that means my resultant velocity, our vector, is 9.3 meters per second, and the heading would be north first, 24 degrees east second. Now part B is asking, how long does it take to reach the opposite shore? Well, you know that the distance in the north direction is 110 meters. Now the boat does not travel 110 meters this way. We don't know this distance, and we don't care to know that distance. If I want to know the time it takes to get here, it's the same time as if you used this speed and this distance together. So if you wanted to use this component of the distance with that component of the velocity, will get the same time as if you figured out this distance over here and its resultant velocity. So the formula is going to be displacement divided by velocity. The question is, which ones are you going to use? So if I'm going to use the displacement north, then I will use the velocity north and get the proper answer. The directions have to match. So I could use the 110 divided by 8.5. That would give me about 12.9 seconds. So we'd probably round that off to 13 seconds, time having no direction. If you'd have worked out whatever this distance is here, divide by the 9.3 meters per second, you will also get 13 seconds. But it's more work, so why not do it in the most efficient way possible?